For as long as you've been interested in the universe, you've been told a lie. It is a beautiful lie, a poetic one, and it is taught in every high school and university physics classroom as if it were gospel. You've heard the phrase, light is both a wave and a particle. It's presented as the ultimate mystery of the subatomic world, a profound duality where nature refuses to pick a side. It sounds deep, it sounds mysterious, and it is absolute nonsense. When people tell you that light is both, they are giving you a wrong analogy. They are trying to force the universe into classical categories that simply do not apply. We are so desperate to understand the unknown by comparing it to the known that we've created a halfway house of language that actually prevents you from learning quantum mechanics. If you believe light is a wave that somehow switches into a particle when you look at it, you aren't learning physics, you're memorizing a confusion. The truth is much more radical and, frankly, much stranger. Light is neither a wave nor a particle. It is not something in between, and it is not a hybrid. Light is a quantum object, a thing that exists in a category of its own for which our everyday language has no word. Because we lack the vocabulary, we use crutches. We say wave because we've seen ripples in a pond, and we say particle because we've seen bullets and billiard balls. But the moment you rely on these analogies, they break. They mislead you into thinking you understand the mechanism when you are actually just looking at a distorted shadow of the math. I am going to show you the actual physics, not the popularized version. To do that, we have to stop trying to visualize what light is and start looking at what it does. The history of science is a 300-year-old game of ping pong where we tried to squeeze light into these classical boxes only to have it explode out of them every single time. We began in the 1700s with Isaac Newton, who was convinced light was a stream of corpuscles, little bullets shooting through space. It explained why shadows are sharp and why light travels in straight lines. It was intuitive, it was mechanical, and it was wrong. But it took a century and a simple piece of cardboard with 2 slits in it to prove just how wrong it was, setting off a chain reaction of confusion that still haunts our textbooks today. By the early 1800s, the bullet theory of light was demolished by a single experiment. Thomas Young took a beam of light and passed it through 2 narrow parallel slits. If light were made of Newton's particles, you would expect to see 2 bright lines on the screen behind the slits, direct impacts from the bullets that made it through. Instead, Young saw a series of alternating bright and dark bands. This is an interference pattern. It is what happens when the peak of one wave meets the peak of another and they reinforce each other, or when a peak meets a trough and they cancel out. The conclusion seemed inescapable. Light is a wave. This wasn't just a guess. James Clerk Maxwell later provided the mathematical backbone, showing that light is an electromagnetic wave, electric and magnetic fields oscillating together through the vacuum. It was elegant, it was complete, and for nearly a century, physicists believed the case was closed. But then the classical categories failed again. When scientists tried to use wave theory to explain black-body radiation, the way hot objects glow, the math produced a literal disaster. It predicted that any hot object, even a toaster, should emit infinite amounts of high-frequency ultraviolet light. This ultraviolet catastrophe was nature's way of screaming that the wave model was fundamentally broken. The fix came from Max Planck, who suggested that energy isn't a continuous flow like a river, but comes in chunks or quanta. He didn't even believe it was real at first. He thought it was a mathematical trick to make the equations work, but Albert Einstein took it further. He looked at the photoelectric effect, the way light knocks electrons off a metal plate, and realized that the intensity of the light didn't matter nearly as much as its frequency. You could shine a dim blue light and get electrons to fly off, but a blindingly bright red light would do nothing. This only makes sense if light consists of discrete packets of energy. If light were a continuous wave, the total energy delivered would eventually knock an electron loose regardless of the color. But it doesn't. Each interaction is a one-on-one event. One photon, one electron. We were right back to particles. Newton was vindicated, but Young's interference pattern hadn't gone anywhere. The bullets were back, but they were somehow still doing wave things. This is where the physics community panicked and invented the dual nature compromise, a pedagogical crutch designed to bridge two ideas that don't actually fit together. The sometimes a wave, sometimes a particle explanation is a surrender. It's an admission that we've stopped trying to understand the world and have started settling for metaphors. Textbooks call this complementarity, suggesting that these two classical pictures are both necessary and mutually exclusive. But if you ask a physicist when exactly light decides to be a wave, or how it knows what kind of measurement you are about to perform, the language becomes vague and philosophical. It stops being science and starts being a riddle. To actually move forward, we have to throw away the classical categories and look at the actual engine of reality, probability amplitudes. In quantum mechanics, we don't describe an object by its position or its waviness. We describe it using a complex number, an amplitude that evolves in time according to very specific mathematical rules. This amplitude isn't a physical wave of matter or a vibrating string. It is a mathematical value that tells us the likelihood of finding that object in a particular state. When you have a quantum object like a photon moving toward a screen, you aren't dealing with a little ball or a spreading ripple. You are dealing with amplitudes. If there are two paths the light can take, such as in the double slit experiment. The quantum object has a probability amplitude for path A and a probability amplitude for path B. These amplitudes are what add together. This is the secret sauce that everyone mislabels. They aren't waves interfering. They are interfering amplitudes. The reason this distinction matters is that it changes the fundamental nature of the question. We are no longer asking how a single particle can be in two places at once, or how a wave can suddenly turn into a solid chunk. We are recognizing that the underlying reality is a mathematical field of possibilities. When these amplitudes overlap, they can strengthen or cancel each other out based on their phase. This math looks exactly like the math we use to describe water waves, which is why we got confused in the first place. But the water wave is a collective motion of trillions of molecules. The probability amplitude is a fundamental property of a single quantum object. We've been confusing the map for the territory for over a century. When we apply the logic of interfering amplitudes to the double slit experiment, the paradoxes of the old duality model simply vanish. In the classical particle view, you imagine a photon choosing one slit or the other, which fails to explain the pattern. In the classical wave view, you imagine the light spreading out and physically passing through both slits like a gas, which fails to explain why the light arrives in discrete individual hits. But as a quantum object, the light does something that cannot be described by either. The probability amplitude for the photon to go through slit A and the amplitude for it to go through slit B both exist simultaneously. They propagate to the screen and add together. Where the sum of these amplitudes is high, the photon is likely to be detected. Where the sum is zero, the photon will never appear. Crucially, the photon doesn't spread out in space like a mist. It remains a singular quantum object, but its behavior, the where of its future, is dictated by these interfering amplitudes. The moment the light hits the screen, we witness what we call a localized detection event. This is the point where people usually get tripped up and say, "Look, it turned into a particle," but it didn't turn into anything. The localized detection event is just the physical manifestation of the amplitude's collapse at a specific coordinate. One photon, one click. The particle-like behavior is simply how the interaction ends in a specific, measurable chunk of energy. The wave-like behavior was never a physical wave. It was just the math of the amplitudes determining the statistical distribution of those clicks. If you don't measure which slit the photon went through, the amplitudes for both paths continue to interfere, and you see the classic stripes. But if you place a detector at the slits to see which way the photon goes, you change the physical situation. You are no longer allowing the amplitudes to evolve undisturbed. By interacting with the photon at the slit, you collapse the amplitude right there. The interference is destroyed not because the light changed its nature, but because your measurement forced a localized detection event earlier in the process. There is no mystery, no choice being made by the light, and no switching between forms. There is only the math of the quantum object being interrupted by an observer. This isn't just a weird quirk of light. If we are to be intellectually honest, we have to admit that this neither nor reality applies to everything. Electrons, which we traditionally think of as solid little pellets of matter with mass and charge, behave exactly the same way. If you fire electrons one by one through a double slit, they don't pile up in two heaps behind the slits. They build up an interference pattern, click by click over time. Does that mean an electron is a wave? No. It means the electron is a quantum object whose behavior is governed by interfering amplitudes. You can do this with atoms. You can do this with large molecules like buckyballs, consisting of 60 carbon atoms. As long as you can keep the object coherent, meaning you don't let the environment or a measurement device kick it and destroy the delicate timing of its amplitudes, it will exhibit interference. The reason you don't see your car or your cat behaving like a wave isn't because they are fundamentally different kinds of matter. It's because they are so large and interact so much with the air and light around them that their probability amplitudes are constantly being collapsed. This process, called decoherence, effectively hides the quantum nature of the world from our oversized, clumsy senses. The pedagogical crutch of wave-particle duality exists because our brains evolved in a classical world. We are hardwired to think in classical categories because, at the scale of hunting mammoths or building houses, things are either localized chunks or spreading oscillations. But nature is under no obligation to be intuitive to a medium-sized primate. When we force quantum mechanics into these old boxes, we don't just get the physics wrong. We open the door to a lot of dangerous nonsense. You've likely seen people take the mysterious nature of duality and use it to claim that reality is subjective, or that your consciousness literally creates the world by looking at it. They argue that if light chooses to be a particle when we observe it, then our minds have power over matter. This is a total misunderstanding born from bad language. Observation in physics isn't about a conscious mind. It's about a physical interaction that collapses a probability amplitude. There is nothing mystical about a photon hitting a detector. By using precise language and sticking to the math of the quantum object, we strip away the magic and find something much more impressive, a universe that follows a set of rules completely alien to our everyday experience. So, why do we keep the myth alive? Why do textbooks continue to print the phrase wave-particle duality in bold letters? Because it is easy. It is a shortcut that lets students solve problems without having to confront the unsettling reality that their mental images of the world are fundamentally flawed. But if you never let go of that pedagogical crutch, you will be forever stuck in a halfway house of mysterious paradoxes. You will spend your life asking if the light is here or there, this or that, when the actual answer is that it is something else entirely. The path to truly understanding quantum mechanics begins the moment you stop trying to visualize it. You must accept that light, and indeed, all matter is a quantum object described by probability amplitudes. These complex numbers aren't just mathematical tools. They are the most accurate description of reality we have ever discovered. We know how they evolve, we know how they interfere, and we know how to use them to predict the behavior of lasers, transistors, and the very stars themselves with breathtaking precision. When you stop asking whether light is a wave or a particle, the paradoxes evaporate. You realize that nature isn't being shy or contradictory. It is simply operating on a logic that doesn't care about our classical categories. The wave is just the math of probability distribution in space. The particle is just the math of a localized detection event. The underlying reality is the quantum object itself, following its own consistent mathematical rules. Quantum mechanics is strange, yes. It is counterintuitive, absolutely. But it is not mystical. It is not a puzzle designed to prove that the world is a dream. It is a rigorous, logical framework that describes a universe far more vast and interesting than the one we see with our eyes. To see it clearly, you have to be willing to drop the analogies. You have to be willing to admit that wave and particle are just ghosts of a classical past. Once you embrace the neither nor, you aren't just memorizing formulas anymore. You are finally beginning to see the world as it actually is. Light is not a wave. Light is not a particle. Light is quantum, and that is more than enough.